Okay, so I'm doing this from home, so you'll have to bear with if I make a mistake. I am not going through this again. It's take a long time to get set up. Anyway, to continue your education, 4.3 where we left off, you can solve statics problems involving friction by using the relationship F is less than or equal to mu r, and we've talked about this and used this quite a bit up until now. You'll have to forgive this starboard stuff here because there's no way of getting rid of that because I'm not connected to a starboard. I'm just using a computer, so just bear with. The force of friction was introduced in chapter 3, or we might not have called it chapter 3. I don't know. I can't remember. But you've done it before in this relationship, okay, with mu being the coefficient of friction and r being the normal reaction. Okay, in statics, you solve problems where there is no motion. When a body is in equilibrium under the action of a number of forces, including friction, you need to consider whether the body is on the point of moving or not. Now, the maximum value of the frictional force F max is equal to mu r, and we've done a lot on that, is reached when the body you are considering is on the point of moving. Then the body is said to be in limiting equilibrium. Really important, if you see that, it's on the verge of doing something, be it tilting, moving, whatever. Okay. In many cases, the force of friction will be less than mu r, as a smaller force is sufficient to prevent motion and to maintain equilibrium. In these situations, the equilibrium is not limiting. You're not on the point of moving. So in this case, in general, the force of friction, if you're not told you're moving or on the point of moving, then all you can say about friction is that it could be less than or equal to mu r unless you know other circumstances. And the direction of the frictional force is opposite to the direction in which the body would move if the friction force was absent. Anyway, let's have a look at this example here. So example 8. A block of mass 3 kilograms rests on a rough horizontal plane. So there's your plane. There is the block. 3 kilograms. The coefficient of friction between the block and the surface is mu equals 0.4. Okay, and when a horizontal force P is applied to the block remains in equilibrium. So let's say it's a pulling force. It doesn't matter if it's a pushing or pulling. As I've talked to you before, it doesn't matter if it's applying this way. I tend to always draw it as a pulling force. So that is P. Okay. And if this was all left like this and there was nothing resisting this, it would accelerate in this direction, the direction of the force, because it's an excess force. So opposing that, because it's rough, is your friction. And it says find the value of P for which the equilibrium is limiting. Well, if it's limiting, you know therefore you are at F max. Okay, F max. So if we look at this, to find out F max, then you know the relationship F max is simply equal to mu r. So we're going to need r. We've got mu already over here. R is the normal reaction. So right angle, normal, that's what normal means. Reaction, what this surface provides. Okay, R. You got the weight component of the block, which is going to be 3g. So the first thing we're going to do is resolve vertically, and let's say upwards is positive. And you tell the examiner that you're using the sum of the net forces equals mass times acceleration. And because we're in limiting equilibrium, we're going to assume that that is equal to 0. But it doesn't matter, it's going to equal 0 anyway in the vertical sense, because it's not moving downwards, it's not moving upwards, so we know it is equal to 0. So the sum of the forces, R being the positive one going upwards, take away the force going downwards is 3g, is equal to 0. So clearly R is 3g. And therefore from that you can find out the F max by simply doing mu, which is 0.4, times by R, which is 3g. So that will give you 1.2 g, or on a calculator 1.2 times 9.8, and it gives you 11.76. So 11.76 newtons. Okay, so that's the maximum the friction can ever provide. So find the value of P, so therefore P can match that, only match it, you can't exceed it. So the question is, the answer for A, P can only ever equal at most 11.6 newtons to remain in limiting equilibrium. So to remain in limiting equilibrium. Limiting equilibrium. Okay, right, then we're on to part B, and part B says find the value of F when P is 8. So I shouldn't, but I am going to use the same diagram. I'm going to call that 8, and you know it hasn't exceeded F max, so this is going to remain in equilibrium. So if that is the case, then find the value of F when P is 8, then F will be 8. Okay, and that is because P isn't greater than, so P isn't greater than or equal to 11.76. So F will be 8 newtons. Okay, so find the value of F when P is 8 newtons. Okay, right, next question over the page. I'll just move this out of the way. Over the page. Right, it says a mass of 8 kilograms rests on a rough horizontal plane. The mass modelled as a particle, and the coefficient of friction between the mass and the plane is 0.5. Find the magnitude of the maximum force P. Right, here we go. Same thing again. You've got horizontal surface, and you've got, it is 8 kilograms. Okay, at least I think that's what it says. Yes, it does underneath all that writing. 8 kilograms. And you got mu is equal to 0.5. Okay, remember mu's got no units to it, it's just a constant, it's just a number. Find the magnitude of the maximum value, the force P, which acts on the mass without causing it to move if P is horizontal. So if P is horizontal, well, we've got to work out what F max will be, because we're after the maximum value that P can be before it's, so in other words, we're in limiting equilibrium. We're going to need to get the friction max, we're going to need to know R up here, and we have simply got the weight is 8g. So to find F max, we're going to resolve vertically upwards is positive, and we're going to use, in the vertical sense, net forces, well, they must sum to 0 because it's certainly not accelerating up and it's not sinking down. Okay, so we've got R is positive and the minus force is the 8g, and that equals 0. So therefore R is clearly 8g newtons. Okay, and then from that we can deduce that F max is equal to mu, which is 0.5 multiplied by R, which is 8g, and that will give you 4g, which in turn is 4 times 9.8 is equal to, estimate 39.2. 39.2 newtons. Okay, so it says maximum, find the maximum value force P which acts on the mass without causing it to move. Well, the max it can get to in limiting equilibrium is that. So you'd finished off that, therefore P could actually equal 39.2 newtons. Okay, now it says B, the force P acts at an angle of 60 degrees above the horizontal. So the same scenario, this is part B. You've got same thing going on the same surface, so mu is going to be the same because the two materials between this and this hasn't changed, so mu is still 0.5. You've got the perpendicular reaction acting like that, and your pulling force, or whatever, the force being applied, is 60 degrees above the horizontal like that. Okay, so that's going to reduce the amount of R needed to keep this in equilibrium. So if you're reducing R, then friction max is going to be reduced. And you'll see that now because you've got the weight component here. Remember, it is 8 kilograms, so it is 8G. We have got F max, that is going to be opposing that, because that's what we want. We want the maximum P, the maximum value that P can be. Well, I'm going to componentalize this to a bit going this way. If I just get the highlighter out. Okay, so a bit going this way. Like that. And a bit going up like that. So the bit going across here horizontally, because it's in the pinch, is P cos 60, and the bit going up is P sin 60. Okay, so resolving vertically using net forces equals 0 in the vertical sense. Therefore, we end up with R is positive, because up is positive, plus the force going up is P sin 60. Sin 60 is root 3 over 2, so that's going to be root 3 times by your P over 2. Take away the opposing force is 8G, and that is equal to 0. So I can see that R is simply equal to 8G, take away root 3 P over 2, and it's that many newtons. Now I'm probably going to neaten this up and make this over 1 at the moment, make it over 2, a common denominator, so it is 16G over 2. Okay, because that's going to allow me just to tinker with this. You don't have to do that, you can use a calculator. Therefore F max, because we're going to try and get the maximum value P can be, and for that this has to provide the maximum opposition resistance. So it equals mu R. Mu is never going to change between these two, as I said before, so it is going to be 0.5, which is a half, multiplied by our 16G minus root 3P, and that is all over 2. So it boils down to 16G minus root 3P all over 4. Okay, and that's newtons. And you'll notice that we still got P in here. So the only way you're going to get rid of that now is by resolving this way, so horizontally. So resolve in the horizontal sense is positive, and net forces equals MA, but we're in limiting equilibrium. We want to find the P, the biggest P can be without this moving, so we're at F max, so it's still not going to move, so it equals 0. Okay, so the only positive force there is your P cos 60, and the opposition is minus F max. Well, this is F max over here, so it is 16G minus root 3 times P, and it is all over. In fact, I'm going to separate that now. It would be an easy now, so I'm going to write that as 4G, and it is 4G, and that is over 4, only because I'm going to need to grab these two together and sort it out. Okay, so I'll just divide by 4 equals 0. Now I know cos 60 is a half, so I'm going to rub that out, so I've got to put it over 2, and I'm going to just get rid of these fractions by timesing through by 4. Okay, and it ends up with 2P minus 16G minus root 3. Whoa. That was lucky, I didn't get rid of the brackets. Very classic. I'm not doing the video again. That a classic mistake. It's minus F max. This is all minus F max. So minus times that makes a positive. Okay, that was lucky. Equals schoolboy error. Equals 0. So I'm going to throw this over, gather these up and factorize. So P is 2 plus root 3, and that is equal to 16G. So P, the biggest P can ever be, obviously using F max, is going to be 16g over 2 plus root 3, and that's going to be an irrational number, root 3, so therefore it's going to be a nasty decimal. So here we go, fraction 16 times 9.8 all over 2 plus root 3 equals, and I get to 3 sig fig because we've used gravity, is 42.0 newtons. Okay, so that's the max P can be if you are angled at 60 degrees. So maximum force of P, which acts on the mass without it moving at 60 degrees, and that's what you get. Okay, over the page. Right, a box of mass 10 kilograms rests in limiting equilibrium again, so we're at F max, on a rough plane inclined at 20 degrees above the horizontal. So there's your 20 degrees, just there, 20 degrees. And here it is, the box. It is 10 kilograms, and it's a rough inclined plane, so I'm going to have to involve friction. Therefore, I'm going to have to provide a normal reaction. There, I'll need the weight going vertically downwards, so that is 10g. And we draw it like this. I mean, you're treating it as like a particle, so that's how we're modelling it. So this is all acting on a pinpoint just here, but in our drawing, that's why we do it. Okay, and that's one of the benefits of using it as a particle. You're neglecting the fact of where this centre of mass is acting, so we don't have to worry about that. Anyway, so 20 degrees above the horizontal. Find the coefficient of friction between these two. So we've got to find mu. It's in limiting equilibrium. So we know that if that was left like this, what would happen? Well, componentalize this. A bit of this force will want to drag it downwards, and a bit of that force, the weight, will want to go like that. So let's just have a look at what these will be. This, as I've always told you, is 20 degrees. It's the same as the inclination. So this will be the force, 10g, and its component is going to be cos 20. And this bit of the force will be 10g, the force, and its component is times by sin 20. If there's nothing else acting on it, it will want to accelerate down here, but it's not. It's in limiting equilibrium because it's a rough plane. So to oppose motion, friction max must be acting upwards. Okay, because we're told it's in limiting equilibrium, and because of those words, we know we're at friction max. Right. So to start us off on this question, we're going to need to resolve perpendicular to the plane. So resolve perpendicular to the plane is up is positive, brackets, underlined. Net forces in that sense, well, we know that's got to equal 0 because it ain't going to float up and it's not going to sink into the ground. So let's have a look at them. We've got R is the only positive one. Take away the 10g and it is cos 20, and there's nothing else that equals 0. So I know that R is equal to 10g cos 20, and I'm not going to work that out because that'll be a nasty decimal, and you never round up halfway through, as well you know. It is that many newtons, so I'm just going to keep it like that. Therefore, F max is simply mu, which we're trying to find, okay, multiplied by this, which is 10g, and it is cos 20, and it is all of that newtons. Okay, so that there is our F max, and we're going to be using that in a second. Okay, so now we're going to resolve up the well, it wants to go downwards, so it doesn't matter. We'll say downwards is positive. Okay, and net forces, and because we know it's not moving because it's in limiting equilibrium, we know it's not accelerating anywhere, so it equals 0. So just looking at that then, the only positive force going downwards is 10g, and it is sin 20, and the one opposing it is F max. So take away your F max, and remember, like I didn't last time, put it in brackets. Not that there's two things going on here, but there might be, and I just overlooked that on the last one. It was nearly catastrophe. Cos 20. Okay, so that force, take away the F max, is equal to 0. So all I've got to do to get this is throw this over, and therefore mu is simply your 10g sin 20, and it is simply divided by your 10g, and it is cos 20. And we've already seen this, that this cancels down, and you tan, it is always tan. If it's just resting in equilibrium to see if it's going to slide down, we've seen this before, that tan of the inclination, if there's no other force acting on it, is actually what the coefficient of friction will be. So working that out and round to 3 sig fig, it should be between 0 and 1. So let's have a look. We've got tan 20 degrees, close brackets, 0.364. 0.364. There's no units. That is what it should be. Okay, and that's the answer. Find the coefficient of friction between that and that. Okay, right. And we've seen that before. If there's no other forces, trying to pull it up or anything like that, and it's just free falling or want to slide down by its own weight, then you can straight away say that mu will always equal tan of the inclination. Let's call it alpha. You've seen that before, I think, in the previous notes when we've talked about F max, but you know, it's worth remembering. Okay, right, over the page. Right, example 11. A parcel of mass 2 kilograms is placed on a rough plane inclined at an angle alpha to the horizontal, where sin alpha is 5/13. Okay, so I've got inclined plane, and I've got alpha, rough plane, inclined angle. In the parcel, may be modelled as a particle, and the coefficient of friction is 1/3, so mu is 1/3. Find the magnitude of the force P acting along the plane, which is just sufficient to prevent the one for sliding up the plane. So here we go. We've got the parcel just there. So find the magnitude of the force P acting along the plane, which is just sufficient to prevent the particle from sliding up the plane. So we've got a P acting up like this, so it's acting along the plane. Okay, and so this is 2 kilograms. You've got its weight coming down here, which is going to be 2g, and we're going to need the R coming out like that. Right, now you have to think about this, because it's just sufficient. It's the word there is really important. Okay, just sufficient to prevent the particle from, okay, sliding up the plane. Now, can you see that just sufficient? I'm trying to get my head around this now myself. So sliding up the plane. So P is just sufficient to stop it from sliding up the plane. Okay. Now it depends which way you're going to put F max here. So find the magnitude. So it's on about moving up the plane. So that needs to be acting downwards to oppose this motion. So that is F max. Okay, acting in that sense. So find the magnitude of the force P acting along the plane, so along the plane, which is just sufficient to prevent the particle from sliding up the plane. Okay, so if I'd put it up there, I could hold it, but it would be just sufficient to stop it sliding down the plane. That is just sufficient to stop it wanting to, on the verge to move over. If P tweaked a little bit more, that would move up the plane, so the F max must be acting in that direction, opposing motion. So we've got to get F max first of all, so obviously we're going to have to resolve perpendicular to the plane, and we've got net forces is equal to 0 in that sense, in the vertical, in a perpendicular sense. So I've got R minus the component of the weight, if you want me to draw it on. Okay, you've got a bit going down there and a bit pulling it back down there like that. Okay. So going back to that, right, the big gang here, as you know, this is alpha. This is your force 2g, and it is cos alpha. And this is your force 2g, and it is sin alpha. Okay, now I always draw, as I've always said, a little snippet of this over here, only because we're told about alpha. You're told specifically here that sin alpha is 5/13, so opposite 5 over hypotenuse is 5/13. So it's a 5, 12, 13 triangle. Okay, so you end up with resolving in the vertical sense, perpendicular sense, sorry, r minus your 2g and your cos alpha. Well, your cos alpha is going to be 12 over, so multiplied by 12 over 13. Okay, and there's nothing else in this sense is equal to 0. So r is equal to basically 24g over 13 newtons, and we're told that mu is equal to 1/3, so therefore I've got F max is equal to mu r, which is 1/3 multiplied 24g over 13, which will give us a third into that gives you 8, so it is 8g over 13 newtons. Okay, so that's what we get as our F max. Now, in either way, that F max is not going to change in part A or part B, because the only way it's going to change is if the angle of the force changes and helps or assists or acts against R. Okay, that's the way that's going to change, or the two surfaces change, or the inclination changes. So none of these are changing, so we can come back to that and use that for part A and B. So for part A in our diagram just here, then we're now going to resolve up the plane is positive. It's on the verge of wanting to move up there. So here we go. We've got net forces is equal to 0 because it's still in the limiting equilibrium. And we end up with net forces, that's going to be P minus your 2g sin alpha. So it is 2g sin alpha 5/13, so 5 over 13. Nothing else acting on there is equal, oh sorry, minus your F max, which is 8g over 13 is equal to 0. So P is simply equal to, this gives you 10g over 13, 18g over 13, throw it over, makes a positive 18g over 13 newtons, which I'll work out P is equal to, and end up with a fraction 18 times 9.8, and it is all over 13 equals SD it, and I get 13.6. So 13.6 newtons. Okay. Now for part B, I'll just squeeze it in just down here. Well, part B, it says the maximum that P can be, a magnitude P, is sufficient to prevent it from sliding down. It's like if it's going to slide down, then F max on this one, I shouldn't really do it in the same diagram, is going to assist it in that way, F max. And that will just what will that have to be to stop it sliding down? So here we go. We end up with resolving up the plane is positive. So net forces is equal to 0 because we're in a limiting equilibrium, and we end up with P plus your F max, which is your 8g over 13, and I've already said that that's going to stay exactly the same because alpha hasn't changed. I'll go through it again. R hasn't changed. P hasn't assisted R, so that's not going to change, and mu hasn't changed between the two surfaces, so that's going to stay the same. Okay, these two added together, take away your 2g sin alpha. Sin alpha is 12 over 13, so times by 12 over 13. Okay, and that is equal to 0. So I end up with that's 24g over 13. Take away from that is 16g over 13. Throw it over. P is equal to 16g over 13. Okay, working that out. 16 times by 9.8 divided by 13, and I end up with 12.1. So P equals 12.1 newtons. Okay, right, just checking this one last time, going up the plane, that's 8G, well, that's the friction max, 2 times that. I used the right thing here, 12, it's not 12, it is, sorry, it is sin. I knew I'd done a mistake here, that's why I'm coming back to it. It's that one there, sorry. It is opposite, it's 5 over 13. Okay, so that gives you 10. 10, take that is 2, so 2G over 13, which now makes that even better. It's 19.6. 19.6 divided by 13 equals SD8, and you get 1.51. 1.51 newtons. Okay, that's more like it, because I didn't, that was my mistake, didn't use sin. 2G sin alpha. Sin alpha was 5 over 13. Okay, so that's the maximum. Maximum could be. Any less than that, it's going to slide down the plane. Any more than that, it's going to slide up the plane. So that's the range. P can be anywhere between here, and it's not going to move. Okay, over the page. Right, a box of mass 1.6 kilograms is placed on a rough plane which is inclined at 45 degrees to the horizontal. The box is kept in equilibrium by a light string which makes an angle of 15 degrees with the line of greatest slope of the inclined plane as shown in the diagram. When the tension of the string is 15 newtons, so I can get rid of that and put 15 newtons. The box is in limiting equilibrium, okay, and about to move up the plane. Well, if it's in limiting equilibrium and want to move up the plane, then F max must be acting in that way there, F max. Okay, find the value of the coefficient of friction between the box and the plane. Well, here we go. We're going to resolve up perpendicular to the plane like that, using net forces equals MA, and we end up with positive, well, we end up with R plus the component of the tension, which is 15, and it'll be sin. Okay, I suppose I ought to draw that on. There we go. So componentalize the tension. You've got a bit going like that and a bit going like that. Back to that, back to that, and back to that. This one will be 15 newtons times by cos 15, and this one will be 15 newtons times by sin 15. So coming back to this, I've got R plus the 15 newtons sin 15, and its weight component, again, I suppose I ought to componentalize that. Okay, so I've got a bit going down here and a bit going down there. So changing this, right, I have 1.6 G, the weight, times by cos 45, and this here is 1.6 G times by sin 45. Okay, I think we've got everything there. So resolving this way, I've got my two positives, and then we take away the weight component, which is your 1.6 G, and it is cos 45, and that is equal to 0. So I've got R is equal to 1.6 G cos 45, and it is take away your 15 sin 15 sin 15. Okay, right, so it's that many newtons. So now I've got my therefore my friction max is equal to mu R, and that's what we're trying to find out, the mu. So here we go, it is going to be simply mu times all of that, which is 1.6 G cos 45 minus 15 sin 15. Okay, so that's our friction max. And we're now going to, because it's in limiting equilibrium and it's wanting to go up the plane, I'm now going to resolve, just draw a line like that. Resolve going up the plane is positive. I end up with net forces is equal to 0 because we're in limiting equilibrium. So I end up with basically 15 cos 15, and it is take away from your F max, which is all that gumph there, which is mu 1.6 G cos 45 minus 15 sin 15, and then I've got to take away also my 1.6 G sin 45. Okay, so I've got my 15 cos 15 going up, pulling me up, and the two bits that's pulling me down is my F max and my weight component, and the sum of those is equal to 0. Now I can rearrange all of that now to give you, throw this over, and mu is simply equal to 15 cos 15, and just make sure I'm not making a mistake, minus 1.6 G sin 45, and it is all divided by your 1.6 G cos 45 minus your 15 sin 15. Right, the answer to that should obviously lie in the range between 0 and 1, and it's got no units. Now just get my calculator out and pray I don't make a mistake, because it's so easy. 15 cos 15, close brackets, take away 1.6 times 9.8 times sin 45, close brackets, go down. It is open brackets 1.6 times 9.8 times cos 45, close brackets, minus 15 sin 15, close brackets. I think that's it. Press equals, and we get an answer that looks realistic. Mu is equal to 0.472. It's got no units to it, and I'm going to store that as A on my calculator because I can't bother to write all that gumph out again if I need to use it. So stow and choose the letter A. Okay, right, it now says part B. So part B, the tension of the string is then reduced to 10 newtons. Determine whether the direction, the magnitude and direction of the force of friction determine if it's going to act up or down. Okay, so looking at this, we've got F max. F max is where are we? F max is this bit here. Okay, it is all of that bit there, so I'm going to work that bit out. So F max is equal to our previous answer times all of this. So calculator, previous answer multiplied by open brackets 1.6, or I have to open brackets again, delete brackets, 1.6 times 9.8, 1.6 times 9.8 times cos 45, close brackets, minus 15 sin 15, close brackets equals, and I get F max as being 3.40 newtons to 3SF. 3SF. So looking at this, I've got the weight component of this, and it says that's been reduced to 10 newtons. This bit here has been reduced to 10 newtons now. So the so we're gonna have to do it all again. Sorry, I'll take that back. It because this has changed, the R has changed. So we've got to do the whole question again, because that will affect your friction max. Okay, so I'm just looking at it to make sure I haven't just read that. The tension of the string is then reduced to 10 newtons. Okay, so Right, so going all the way up here, I suppose I could rub things out. Yeah, so I've got, that's it, so 10, it's still at 15 degrees, so that's 10 there. This is quite bad of me, I know. And then R is equal to 10 goes there, and then F max is equal to mu, and 10 goes there. Saves me how to write all that again, that's good, isn't it? Right, I can rub this out. Okay, rub this out because, oh no, edit undo. How do I get back to there? File, edit, undo. Because mu is going to stay the same, doesn't matter what goes on here, but F max is going to change, just mu is different. Okay, so now all I've got to do is come into here and get my new F max. Mu will stay the same. Okay, so I've got my mu now, and calculator, thank God I stored it. So alpha A equals, that's it, and then times it by open brackets 1.6 multiplied by 9.8 multiplied by cos 45 close brackets minus 10, and it is sin 15 close brackets equals, so I get that to be 5.11 newtons, the F max, because obviously reducing this increases the amount R that's needed. You increase R and therefore F max is mu R, the F max is going to increase. So that makes sense, I'm happy with that. Right, it says determine the magnitude and direction of the frictional force. So let's look at the pulling force. The pulling force is this bit here, okay? It's pulling it up. So we now need to work out what is 10 cos 15. So the pulling force is 10 cos 15. So we're going to work that out. It is equal to 10 cos 15 close brackets equals SD it, and with 9.66 newtons rounded up to 3 sig fig. So okay, right, so determine the magnitude and direction of the force of friction, if that's the case. Right, the tension of the string is then reduced to 10 newtons. Okay, something's gone wrong here. What have I done wrong? So F max is equal to 5.11 newtons. Okay, I'm happy with that. It's got the, yeah, okay. So sorry, that's the pulling force. We got that. I didn't need to work that out. So now I'll rephrase that. Okay, so we're just going to resolve vertically upwards now, is the better way to do it, because you've got the weight component. Okay, so the net forces is equal to 0. So net forces going up is going to be the tension going upwards is actually T, which is 10, and it is cos 15. The opposing that compared to the weight component. That's what you want to compare it with, the weight component. Forget about F max. So take away the weight component is your 1.6 G, and it is sin 45. Sin 45. We need to know what that equals. Is it positive or negative? If it's positive, it means there's an excess force there, and the friction max will have to be within that range to make sure that it doesn't move upwards. Or if it's wanting to pull it down, then F max will be acting upwards. So it is the result of this that we need to look at. So calculator out. Okay, hope that makes sense. 10 cos 15, take away open brackets 1.6 times 9.8 times sin 45, close brackets, and there should be there equals, and I get an answer of, it is actually negative 1.43 newtons. Okay, 1.43 newtons ran to 3 sig fig. So what is that telling us? Well, the pulling force going up and the weight component going down, there's more weight wanting to pull it down, so therefore you can clearly see that we're not at Fmax, because Fmax can provide a maximum of 5.11 newtons. So therefore the friction will be acting up the plane, therefore friction will be aiding the pulling force. Friction will be acting up the plane. Okay, assisting the tension. And is 1.43 newtons. Okay, so we aren't in limiting equilibrium, we are going to be stationary, but you're going to need that much going upwards to assist it. Okay, so we only had to look at, for this question, we only had to look at the tension component going up, the weight component dragging it down, and that gives us this discrepancy of 1.4 newtons. We said up is positive, so it's acting downwards. There's more weight pulling it down, so friction is going to need to aid it by acting upwards. We worked out our new Fmax. Fmax was new because we had a different tension, so we had to work out a new Fmax, but the mu stayed the same. The important thing was that mu stayed the same, so we could use that from part A, put it back into here, and the 10 was the only thing that changed. It gave us this new Fmax, and you can see this is within the tolerance, so it's not, Fmax can only maximum ever provide that, and that's certainly that's within it. Okay, over the page. Right, there's the exercise. Now I want you to give it your best shot, give it a go. Any problems at any stage, then I want you to email me. I'll do a video if I need to for help. Okay, but I'm hoping that's going to get you on the way with more of these videos so you can continue your lessons. All right, stay safe.